All right, let's get started. From today, we're going to start a new chapter. Okay, so the first 5 weeks we went through chapter 1, chapter 2, especially chapter 2. Today we're going to start chapter 3, which is called propagation of error. Okay, so chapter 3 is pretty short. I think hopefully we can finish this chapter today. Okay. And chapter 4 is going to be a long chapter again, which is also very, very important. Okay. I hope you are doing well with your homework number 1. Okay. Again, if you have any questions, just let me know. Okay. All right. So propagation of error. Okay. So what is error? Okay. So any measurement procedure will contains error. For example, we use a scale to measure the weight of a concrete blocks. Okay, so the measured value will be somehow different from the true value of the concrete block. Okay, so this is example of error. So measured value generally differ somewhat from the true value that are being measured. The true value could be a known value or could be unknown to us. Error in the measurement will in turn produce errors in the calculated values. For example, if we take 5 measurement of the weight of the concrete blocks, the mean value of this 5 measurement will produce the error in the calculated mean value. Okay. So definition, when error in measurement produce errors in calculated values, such as the mean, or standard deviation, then we see that the error is propagated from the measurement to the calculated value. Okay, so this is what we call propagation of error. Okay. So for example, we weigh a rock on a scale and get these following 5 measurements. Okay, so 251.3. So we have 5 measurements. And this measurement will, as we can see, differ from each other. And it is unlikely that any of these measurements is exactly equal to the true mass of the rock. So the true mass of the rock, in this case, we do not know. It's not tell us. Okay, and the error in the measured value is the difference between a measured value, such as 251.3 or 252.5. Okay, so let's measure the value and the true value. Again, the true value could be known, could be unknown to us. And difference between measured value and the true value, we call that error. Okay. And error has composed of 2 parts. Okay, the first part is called bias or systematic error, and the second part is called random error. Okay, so let's look at these 2 parts of error. So bias is the part that the error that is the same for every single measurement. For example, we use a scale to measure the weight of the rock, and every time the scale will give a higher value or overestimate the true value. For example, if the scale is not calibrated well, then it will give overestimate or underestimation. Okay, so we call that type of error bias. If we recalibrate the scale, then the bias will become 0. Okay, so that's the first part of error. We call that bias or systematic error. The second part of error is called random error. So that's the error that varies from measurement to measurement. And if they take the average of this measurement, it will average out to 0 in the long run. Okay. So any measurement can be considered to be the sum of the true value plus contribution from each of these two components of error. Okay, so the measurement value will equal to true value plus the bias or systematic error plus the random error. Okay. So here said we are interested in accuracy. So accuracy is another word which is correlated to bias or the systematic error. Okay, so accuracy is determined by bias. The smaller the bias, so we say it's more accurate. The measuring process is more accurate. Okay. If the bias is 0, the measuring process is said to be unbiased. For example, if we recalibrate the scale, the bias will be 0, then we say the scale is biased. So accuracy is determined by bias. We are also interested in precision. Okay, so bias and precision, you may think they are similar words or the same words, but in this chapter, they have different meanings. Okay, again, accuracy is determined by the bias. The smaller the bias, we call that more accurate or have high accuracy. Precision is determined by uncertainty. Okay. Precision refers to the degree of which repeated measurement of the same quantity tend to agree with each other. Okay, so basically precision measure the spread or difference between each single measurements. If repeated measurement come out near the same every time, so that's a very small difference between single measurement, then we say the precision is high. Okay, so that's different from accuracy. So let's look at this. Okay, so here shows 4 cases, all about parts of error. So for all these 4 cases, these are the measurement. We have around 10 measurement for each case. Okay, and we know the true value. The true value is shown here. Okay, and we have A, B, C, D 4 cases. Okay, and then let's compare the accuracy and uncertainty and precision for each of these 4 measurements. Okay. So let me share my iPad with you. Sorry, give me a second. Okay. All right, so this is the screen of my iPad. Let's look at the first case. Okay. So in the first case, we have 10 measurements. Okay. And the first thing we can notice is the points are pretty much close together compared to the case C and case D especially. So the points are close to each other. So we call that it has high precision or it has a smaller uncertainty. Okay. So again, for the first case, the first thing we can see is points close together. Okay, so that's a small variance between each measurements, smaller. Okay, so we can see it has smaller uncertainty. Or we can call that as high precision. Okay. Another thing we can notice is the true value is pretty much close to the average value of these 10 measurements. Okay. So in other words, the 10 measurements are centered near the true value. Okay. So the 10 measurements are centered near true value. True value. So we call that the bias is small. So small bias. We can also call that as high accuracy. Okay, high accuracy. Okay. All right, so we talk about uncertainty, precision, bias, and accuracy. Okay, so when the measurement are close together, it doesn't care about the difference to the true value. As long as the points are close to each other, we see the uncertainty is small. Okay, we have another parameter to describe uncertainty, which is the standard deviation, which we'll talk in a moment. We can also see the precision is high precision. Okay, the bias or the accuracy is determined by the difference between the true value and the measured value. Okay, because in the first case, the center of the measurements are pretty much close to the true value. So we see the bias is small, and we call that high accuracy. Okay. All right. For the second case, the spread is also small. Okay, the points are close together. So points close to each other. So because the points are close to each other, we call that small uncertainty and high precision. Okay. So small uncertainty. Okay. Or high precision. Okay. So then let's compare the center of the measurement or the average of the measurement with the true value. Okay. The center is here, around here. So which is far away from the true value. Okay. So we see the bias is large. So large bias. Okay. We can also see it has low accuracy. Low accuracy. Okay. So the second case has high precision but low accuracy. Okay. And then look at case C. In case C, the spread is big, much bigger than A and B. So we see that it has high uncertainty. Okay. Or low precision. Okay. However, the mean value, which is around here, so the mean value of this 10 measurement in case C is very close to the true value. Okay. So as a result, we call that small bias and high accuracy. And the case D, because the case D, the spread is big, the 10 measurements are very different to each other. So we said that it has a large uncertainty. Or low precision. Okay. The bias is also large. Okay. Again, the bias is charged by the difference between the true value and the measured one. Okay. Because the average of this 10 measurement is around here. So the difference between the true value and the average value is big. So in case D, we see it has a large bias. Okay. We can also call that has low accuracy. All right. So from here, we could have a feeling about understanding of what is uncertainty, precision, accuracy, and the bias. Okay. So they are judged by either the spread of the measurement or the difference between the true value and the mean of the measurement. Okay. And the definition is shown here. What is accuracy and what is precision? Okay, so let's continue. Here also has 4 cases. The difference between these 4 cases and the previous 4 cases is we do not know the true value. Okay, here we know the true value, but here we do not know the true value. It is very common. In reality, very often we do not know the true value of our measurement. Okay, so because of that, we can give an idea of the uncertainty or the precision of this measurement, because uncertainty and precision is judged by the difference of the measurement. And we can easily see the difference of the measurement is big or small. So in case A has small uncertainty, okay, or low precision. Okay, and case B also has small uncertainty and low precision. And case D, we have high uncertainty or small uncertainty, high precision, right? High precision, sorry. Case C is high uncertainty, low precision. And so does case D. Case D also has high uncertainty and a low precision. Okay. However, because we do not know the true value, okay, so we do not know the accuracy or the bias. Okay, so we do not know about bias or accuracy. Okay, so because we do not know the true value, okay, because the bias and accuracy is determined by the difference between the true value and the measured value. Okay. So in summary, so a measured value is a random variables with a mean value of mu and standard deviation of sigma. Okay, And from chapter 2, we know how to calculate the mean value and the standard deviation. Okay, and we also know the standard deviation is kind of measurement of the spread. Okay, so the bias in the measuring process is the difference between the mean measurement and the true value. Okay, so the bias is equal to mean value mu minus true value, and the uncertainty is measuring the process. In the measuring process is the standard deviation. Okay, so we use standard deviation sigma to quantify the uncertainty. All right. So the smaller the bias, okay, we see is more accurate. The measuring process is more accurate. Okay, so smaller the bias, measurement is more accurate, and the smaller the uncertainty, we see the measuring process is more precise. Okay, so here we have two more parameters, so sigma and the mean value. All right, so the random error, including uncertainty, okay, and uncertainty we use sigma or standard deviation to quantify that. Okay, the smaller the uncertainty, we say it is more precise or high precision. So we use precision to describe uncertainty or sigma. Okay. The second part is the bias. Okay, so for bias, we use the difference between the mean value and the true value. Okay, so mean value minus true value used to describe bias. Okay, the smaller the difference between mean value and the true value, we say it has small bias, and we call that more accurate. So we use accuracy to describe the bias. All right. So you may take some time to familiar with this word. Okay. So try to know the difference between precision, accuracy, uncertainty, and bias. Okay. And then we use standard deviation sigma to describe uncertainty and precision. And we use the difference between mean value and true value to describe bias and accuracy. Okay. All right. So this is something important for you to understand and remember. Okay. Any questions or comments for this?
First, I have a question.
Yeah, sure.
So bias, is it absolute value, as in like it's always positive, or can it be negative?
Oh, it could be positive or negative. Definitely. Yeah. Yeah.
So just be like plus or minus and all that.
Yeah, sure. Yeah, as you can see in the example later, the bias we use, plus or minus.
Okay, got it.
Okay, thank you. All right. So let's look at an example. So here we have a lab sample of gas. So it's known to have a carbon monoxide, CO concentration of 50 ppm. Okay, ppm is parts per million. So the true value is known, told us 50 ppm. A spectral photometer is used to take 5 independent measurements of this concentration. And here are the 5 measurements. Okay, so estimate the bias and also the uncertainty for the measurement. Okay, so the bias is difference between mean value and true value. Okay, so the true value is known, 50, given us. The mean value, we can easily calculate that. So So first part, the bias. Okay. Bias is mean value minus true value. So the mean value, just take the average of these 5 measurements. Okay. So it turned out to be 50.4 minus the true value 50. So the bias is 0.4 ppm. Okay. And uncertainty, so you can see from here. So uncertainty, we use sigma, which is the standard deviation to quantify that. Okay.
Professor,
Yeah.
can you zoom out just a tiny bit?
Zoom
out.
out. Okay. All right. It's okay?
Yeah, right there. Thank you.
Okay. All right. So we use sigma to quantify the standard uncertainty. But the sigma, it is, remember, it's called population standard deviation. Okay. But here we only have 5 measurement. Okay. So we can use sample standard deviation to estimate the sigma, which is population standard deviation. So sample standard deviation, we call that S, right? So S, the equation for S is this, n minus 1. So the sum of xi squared minus n, the mean value of the measurement squared. Okay, so the n is 5, right? The mean value is 50.4. Okay. Yeah, we use this equation to calculate the S sample standard deviation. So 2.8 ppm. Okay, so the bias is 0.4 and the uncertainty is 2.8. Okay. One more thing I forgot is the mean value should be the population mean value. Okay, and the sigma should also be population mean. Okay, but in our case, we do not know the population mean and population sigma. So instead, we use sample. So this is sample mean. Sample mean n. Okay, and we use the sample standard deviation. So which is S to estimate that. Okay. So again, so if say we have n measurements which are independent, all these measurements made by the same process on the same quantity, then the sample standard deviation S can be used to estimate uncertainty. Okay, and is that the estimation sometimes could be crude, especially when the sample size is small. Okay. If the true value is known, we can use the sample mean to estimate the bias. Okay. Yeah, here should be the sample mean. Okay, sample mean value. But if the true value is unknown, then we do not know the bias. So true value is unknown, the bias cannot be estimated from repeated measurement. Okay. And here is the same example. So the spectral photometer has been recalibrated. Okay, so that means the bias right now is become 0. So we may assume that the bias is negligible. Spectral photometer is not used to measure the concentration in another gas sample. And the measurement is 55.1 ppm. Okay. How should this measurement be expressed? So the uncertainty is still 2.8 ppm, okay, from the last slides. Because the measured value is equal to the true value plus bias plus uncertainty. Okay, and the bias is 0 because it is recalibrated. The bias is 0. So we see the measurement can be expressed as 55.1 plus minus the uncertainty, which is 2.8 ppm. Okay, so pay attention. We use plus minus here. Okay, so the uncertainty is 2.8, and we use the 50.5 plus minus 2.8 ppm to describe the measurement. Okay, let me see if anybody has questions. Let's see some chats. Okay, so that is the first section for chapter number 3. Okay, so I think the idea is simple. Okay. Just know the error has 2 parts. Okay, the error, the bias, okay, and also the random error. Okay, and you should know what is uncertainty, what is accuracy, what is precision, and whether you use sigma or the mean value to describe these 2 types of errors. Okay. The next section is called linear combination of measurements. Okay, if we have measurement x, and we have a constant c here, and then the standard deviation sigma cx, okay, the standard deviation of cx is equal to the absolute value of c times sigma x. Okay, and if we have n independent measurement, and for each measurement we have a different constant c1, c2, and cn before them, and then the standard deviation of c1 x1 plus this is ... plus cn xn is equal to this equation. Okay, so the constant value becomes square. Okay, c1 to the power of 2 sigma x1 square plus this is again ... okay, cn square sigma xn square, and we take the square root of it. Okay. Okay, so here is another example, a severe measuring the parameter of rectangular lot. So he measured 2 adjacent sides to be 50.11 plus minus 0.05 meter. Okay. So this is x 50.11 plus minus 0.05 meter. Okay. And the other side is 75 12 plus minus 0.08 meter. And these 2 measurements are independent. Estimate the parameter of a lot and find the uncertainty of the estimate. Okay, so the parameter is equal to 2x plus 2y, right? Okay, easy. So we just add 2 times x, 5011 plus 2y, 75.12. So the parameter is this. Okay, and then for the uncertainty, of the parameter p, okay, is equal to the uncertainty of 2x plus 2y. Okay, so we have a constant before x and y, so we can think this constant as the c in the previous equations. Okay, right. So c is 2. So based on the equation in the previous slides, that's 2 squared times sigma x squared plus 2 squared sigma y squared. Okay, and the sigma x, just tell you, just sigma x 0.05, and sigma y is 0.08. Okay, so it turned out the uncertainty for the parameter is 0.19 meter. So we describe the parameter p is equal to 250.64, which is here, plus minus 0.1 meter. Okay, so again, is plus minus uncertainty. All right. If we have repeated measurement, and this repeated measurement x1, xn are independent, okay, and then the following two equation will hold true. Okay, so each with a mean value of mu, so each measurement has mean value of mu and the standard deviation of sigma. Okay, and then the sample mean, okay, is the measurement of mean value. So mean value of the sample mean. All right. So again, so this could be kind of awkward. So we call that mean value of sample mean. Does not change. Okay. So the mean value of sample mean is the same, equal to mean value mu, the mean value of each single measurement. Okay. The interesting part is the sigma, or the uncertainty. So the uncertainty of the sample mean again, we call that uncertainty of sample mean, becomes smaller. Okay, is equal to sigma over square root of n. N is the sample size. Okay, so from here we can see when we increase the number of measurements. Okay, so when we increase the number of measurements, okay, the precision will increase. Why? Because the sigma goes down, right? So we increase the number of n, right? N become bigger, so the sigma will become smaller. So we call that precision goes up. Okay. But the accuracy will not change. not change. Okay. Again, what defines accuracy? So accuracy is defined as difference between the true value and the mean value. Okay. Okay. So both the true value and the mean value does not change when we increase the number of measurements. So the accuracy will not change. Will not change. But precision will increase. Let's look at another example here. The length of a component is to be measured by a process whose uncertainty is 0.05 centimeter. So 25 independent measurement and the average of those is used to estimate the length. Okay. So what will the uncertainty be? So uncertainty of the mean value based on the previous equation is equal to sigma over square root of n. Okay. The sigma tells us 0.05. Square root of n, we have 25 measurements. Okay. It becomes 2.01 centimeter. Okay. So how much more precise is the average of this 25 measurement than a single measurement? So before, for single measurement, it is 0.05. And now we have 0.01. Okay, so it is 5 times more precise. Okay, so 5 times more precise than single measurement. Okay, so again, increase number of measurements. Okay, the precision will increase because the sigma will become smaller due to this equation. But the accuracy will not change. Yeah. All right. All right. Any questions or comments about this? Here shows a special situation. So repeated measurement with differentiating uncertainty. If x and y are independent measurement of the same quantity, okay, and this measurement has different uncertainty, sigma x and sigma y. Okay. For example, if we try to measure the weight of a rock using 2 different scales, okay, so scale x and scale y, okay, maybe scale x is more accurate or less accurate than scale y. So these 2 scales has different sigma. Okay, if that's the case, then the weighted average of x and y with the smallest uncertainty is given by this equation. Okay, so we have C best, which is a constant, which can be calculated based on this equation. Okay. So basically, using this method, it will give more weight for the measurement with higher precision. Okay. For example, we use 2 scales. We give more weight to the scale which is more accurate than the scale which is less accurate. Okay. Again, this is a special situation when we do the measurement using two measurements for the same quantity, and if they have a different uncertainty, and then we're gonna use this equation. Okay. The next part is about linear combination of dependent measurements. Okay, again, this is not very common. If the measurements are not independent, if they are dependent, okay, and we have constant before each measurement, then this will give up this equation, an equation will give upper bound of the uncertainty. Okay, this is less or equal to, this is C1, the absolute value of C1 sigma x1. This is not L, again, it's dot, dot, dot. Okay. And this is also dot, dot, dot. Okay. If the measurements are independent, then this equation holds true. This is a previous example, trying to measure the parameter of the lot, okay, x and y. Okay. For x, 50.11 plus minus 0.05, and for y it is this. Okay. And if we do not know these two measurements, x, y are independent, so not necessarily independent from the conservative estimate of the uncertainty. So we're gonna use this equation. So uncertainty of the parameter 2x plus 2y will be less or equal to, again, using this equation. So absolute value of C1, so C1 is 2 sigma x plus absolute value of C2, also 2 sigma y. Okay, and sigma x is 0.05, sigma y is 0.08. Okay, so that turned out to be 0.26 meter. Okay, so if we do not know they are independent or not, then the sigma of the parameter is should be less than or equal to 0.26. Okay. If they are dependent, independent from the previous example, okay, if they are independent, then the sigma is 0.19. Okay, so smaller than 0.26. The last part for chapter 3, we have around 9 slides remaining. Okay, it's called uncertainty for functions of one measurement. Okay, and we call that propagation of error. If x is a measurement, and if the uncertainty of the measurement x is small, we call that sigma x. Okay, and if u is a function of x, okay, and then this is the equation for propagation of error. Okay, so sigma u, again, u is a function of x, will equal to the derivative du dx, which is absolute value times sigma x. Okay, and when we calculate du dx, we should plug in an x at observed measurement of x. Okay, so we should do some calculation for derivative, and then we plug measurement of x into that equation to calculate sigma u. Okay. And we call this propagation error formula. And this chapter 3, is called propagation of error. Okay. Here talk about relative uncertainty. Okay, so relative uncertainty for a function of one measurement. If U is the measurement, okay, which the true value is mu U, okay, and the uncertainty is sigma U. And then the relative uncertainty is this. So sigma U over mu U. Okay. And because this is the ratio of sigma and mu, this quantity has no unit. So this is a unitless quantity. So relative uncertainty is a unitless quantity. Okay. And we can use a percent to describe that. Okay. And in practice, if the bias is small enough, we can calculate the relative uncertainty with sigma U over U. Okay. So here is the U is a single measurement. For example, here, so radius R of the sphere, for R, it is measured to be 3.00 plus minus 0.001 centimeter. Okay, so ask the volume of the sphere and its uncertainty. So the volume of the sphere is a function of R, right? And the function is this. So the volume is equal to 4 pi R cubic over 3. Okay? So we estimate the weight, the volume weight is 4 pi, we plug R equal to 3 into that equation. So we get the volume to be this much. So next, we need to figure out sigma R, uncertainty of the, no uncertainty. So uncertainty of the V, the volume. And based on the equation for propagation of error, so we use equation this. Okay. So U is a function of X. And here in our example, the volume is function of R. Okay. So that's why we get this equation. We need to calculate dV dr, and dV dr is this. Okay. So 4 pi R squared. And we plug in R equal to 3 into 4 pi R squared. So we calculate dV dr equal to 36 pi. Okay. So that is dV dr is 36 pi. And sigma R is given, which is 0.001 centimeter. So sigma U, the uncertainty of, sigma V, uncertainty of the volume, become 1.056. So we describe the volume of the sphere to be this. Okay, so that is sigma V. So we use the propagation of error formula in this example. Okay, we need to calculate the derivative du dx. Yeah. And in our case, it is dv dr here. All right. Any question about this? All right. And these slides talk about how to calculate relative uncertainty. Okay, so relative uncertainty is sigma u over u. Okay, so right, so we could use one of these two methods to calculate the relative uncertainty, depending on which one is easier for that specific question. Okay, we can calculate sigma u use equation 3.10, okay, which is here, 3.10. Okay, so we calculate sigma u, use this equation, and then divide by u. So that's one way to do that. Okay. Or we could calculate the natural log of u, which is ln u. So, and then use equation 3.10 to find from sigma natural log u. Okay, and that is equal to the relative uncertainty. Okay, the reason for that, why we can use the second method, is because sigma natural log u, okay, we can think natural log u as a function of u, right? So that's based on equation 3.10 is equal to derivative log u du sigma u. Okay, and it will be simplified as this. Sigma u, right? And it will be further simplified as sigma u u. Okay, so that is the relative uncertainty. Okay, so again, which method to use is depending on which one is easier to solve for certain problem. Okay, so again, relative uncertainty is a number with no units. So go back to the sphere problems, asking what is relative uncertainty for the sphere. Okay, so the volume from the first part is calculated to be this much. Okay, and relative uncertainty will be sigma v divided by v. Okay, and sigma v is 1.056. Okay, this, and v is 113. Okay, so relative uncertainty is 0.00934. We can use it as a percentage. So the volume can be rewrite as equal to 113.097 cubic centimeter plus minus 0.934%. Okay, so that is relative uncertainty. All right. And here shows the most complicated part, which we have an independent measurements. Okay, and the U has different functions, has more than one measurements. Okay, so if that's the case, then we should do partial derivatives. Okay, this is partial derivatives for x1, for x2, and for xn. Okay, That's the equation when we have more than one measurements for the function of u. Okay. If these measurements are not independent, these questions valid when the measurements are independent. If they are not independent, okay, and then this will hold true. Okay, it's a conservative estimate for function u. Okay, when u is a function of x1, x2, and xn. Okay, the calculation will be very complicated because we need to do partial derivative. So we do not expect to see much of these kind of problems in the exams, but you should understand it. Okay. This is about more words about uncertainty for the function of dependent measurements. Okay. And lastly, let's look at an example. Okay. So this is the same rectangular lot. Not the same, but similar. Okay. So two perpendicular sides of rectangular are measured to be x 2.0 plus minus 0.1 and y 3.2 plus minus 0.2 centimeter. Okay. So asking the absolute uncertainty for the area. Okay. This is a function. The area is A is equal to x times y, right? And it has two measurements, x and y. X has uncertainty of this, and y, sorry, this, and y has uncertainty of that. Okay. So we should use uncertainty for function of u, which is equal to a partial derivative for x sigma x1 square. Sorry. So partial derivative for the second measurement, x2 sigma x2 squared. And here, the function is a, right? And a equal to x times y. Okay. So plug in the equation. Okay. There will be partial derivative for a for x measurement square sigma x square plus partial derivative a for y square sigma y square. Okay, and here sigma x partial derivative of a for x, okay, is equal to y, and plug in y equal to 3.2, and the partial derivative for y based on this equation is equal to x, okay, so which is equal to 2.0. Okay, and then we can plug in the number, so 3.2 here, 2.0 here, sigma x is 0.01, and sigma y is 0.2. So square is 0.04. Okay, so that is 0.2 square. So this is 0.1 square. Okay, so the uncertainty for the area is 0.15122. Okay, so that's the end for chapter 3, which is pretty short compared to other chapters. So we understand the measurement error, so which consists two parts. Okay, and also we talk about different contribution to the measurement error, and then the linear combination of measurement for both independent and dependent case, but you should focus on the independent case. And then we consider repeated measurement with different uncertainties. And then we discuss uncertainty for function of one measurement and more than one measurement. Okay. So yeah, this is chapter 3.